Hey there, and welcome. Today, we're going to tackle a really fundamental puzzle in physics. We're going on a little journey, from the simplest possible movement, just a straight line, all the way to the perfect looping arc of an orbit. And you know what? We're going to find out they're governed by the exact same super elegant rules. So, how are those two things connected? Let's dive in. I mean, really think about that for a second. The moon is just hurtling through the void at, what, over 2,000 miles an hour. There's nothing you can see holding it there, so what's stopping it from just shooting off in a straight line forever and ever? Well, the answer to that huge cosmic question is actually the exact same answer that explains why a baseball curves or why you feel pushed to the side when you're in a turning car. It all boils down to one powerful master equation. And here it is, F equals ma. You've probably seen it before. Outside of maybe E equals mc squared, this is the most famous equation in all of physics. This is Newton's second law of motion, and believe me, it is the key that unlocks everything we're talking about today. Okay, so force equals mass times acceleration. It looks so simple, right? But these three little letters, they describe the relationship between why things move, what is moving, and how that movement actually changes. So let's break this down piece by piece. So first up, you've got F for force. The easiest way to think about force is just as a push or a pull. That's it. It's the engine of all change in the universe. You know, gravity is a force. Friction, that's a force. The wind pushing against a sail, that's a force too. Next, we've got M for mass. Now, mass isn't the same thing as weight. It's really the amount of stuff an object is made of. But more importantly, it's a measure of inertia, which is just a fancy word for how much an object resists having its motion changed. More stuff means it's harder to get moving, and, well, it's harder to stop once it is. And finally, we have A for acceleration. Now, this one's key. Acceleration is any, and I mean any, change in motion. Most of us just think of acceleration as speeding up, hitting the gas. But in physics, slowing down is also a type of acceleration. And this is the most important part for where we're going next, so is simply changing direction. All right, let's see how all these pieces fit together. Imagine you give the exact same push, the same force, to a bicycle, and then you turn around and give that same push to a car. The bicycle, with its pretty low mass, is going to accelerate like crazy, right? But the car, with its huge mass, it's barely even going to budge. It's a perfect example. The same push creates totally different results, and it's all because of mass. Okay, so this is the crucial point. If there is one thing you take away from this section, let it be this. Whichever way you push something, that is the direction it accelerates. The push and the change in motion are perfectly, totally linked. Always. No exceptions. Now, let's take that one simple rule and see how it can create something way more complex and honestly kind of beautiful. We're going to take that key idea, that force and acceleration are always in the same direction, and see what happens when we start applying it to circles. And this is the big question, the pivot point. We've already figured out that a push from behind makes you go faster. A push from the front, well, that makes you slow down. But what if the object is already moving forward and you start pushing it from the side? Just picture it for a second. You have an object, and it's trying its best to go in a straight line. But at every single moment, there is a constant force pulling it exactly sideways, at a perfect 90-degree angle to the direction it wants to go. Now, think about what that means. Since this force isn't pushing from behind or pushing from the front, it can't actually change the object's speed. All it can do, its only job, is to change its direction. It's just a constant, gentle nudge sideways, forcing the path to curve, moment after moment after moment. And if that perpendicular force stays constant, the result is a perfect circle. The object is always trying to fly off in a straight line, but that sideways force is always pulling it back toward the center. This is exactly what's happening with the moon. Its forward motion wants it to fly away, but Earth's gravity is that constant, perpendicular force pulling it into a nearly circular orbit. See? It all connects. So, now that we know why things move in circles, let's look at the rules that actually govern that motion. Like, how do you control the speed or the tightness of that curve? This table here pretty much breaks it down, and it reveals a really simple relationship. Just look at that middle column. If you want to go faster but stay in the same circle, you need more force. If you want to make the circle tighter but at the same speed, you need more force. And if you want to swing a heavier object around at the same speed in the same circle, Yep, you guessed it. You need more force. This is basically the one unifying principle of going in a circle. Think about a race car. For it to take a really tight turn at a super high speed, it needs an immense amount of force pulling it toward the center. Force from the friction of its tires and the downforce from its wings. Any change that makes that turn more demanding requires a stronger central pull. Period.
Okay, let's bring this all home. Let's see how these simple ideas explain the motion that we see all around us, every single day.
So, here are the big ideas, the absolute core takeaways. Number 1, a push causes a change in motion in the exact same direction as the push. Number 2, if that push is always sideways to the direction of travel, you're going to get a curve. And number 3, to make that curve more extreme in any way, faster, tighter, or heavier, you've got to increase that sideways push. That's really the whole shebang.
And I'll leave you with a little something to chew on. You're in a car, and it takes a sharp left turn. You feel like you're being thrown against the door on your right. But, based on everything we've just talked about, is the force on you really pushing you to the right? Or is the car door actually pushing you to the left? Think about it.